In the last section, we laid down the basics of our language for talking about networks by looking at graph theory. In this module, we're going to continue to expand our vocabulary, but this time focusing on how we model the connectivity of a node or between nodes within a graph. As we previously mentioned, connectivity is a key concept within the network paradigm. We often try to measure the significance of a thing in terms of the quantity of one of its properties. But within networks, how connected an individual node is becomes a key metric of its significance within the network. So an important question we will often be asking is how connected is any given node in the network? And this is termed its degree of connectivity. The degree of a node in a network is a measure of the number of connections it has to other nodes. This degree of connectivity can be interpreted in terms of the immediate likelihood of a node catching whatever is flowing through the network. So for example, the higher your degree within a given social network, the more likely you are to hear about some juicy piece of gossip that's spreading, because you have many more channels through which to intercept it. Of course, this works both ways, as it might not be juicy gossip that's spreading on the network, but instead a virus. Connectivity is often interpreted as a positive thing, but it might not always be so. If we're analyzing an undirected and unweighted graph, a node's degree of connectivity will then simply be a summation of all the links that node has. If the graph is directed, then we can refine our analysis by dividing this into a measure of the amount of in and out links. So returning to our previous example of nations trading, the in degree of any node would be the total number of import relations it has with other nations, and the out degree would be the total number of export relations it has. If this is a weighted graph, we can then of course refine our model further by placing quantitative values on each edge. If an edge exists between node A and B, then we say they are adjacent. So if we're talking about a map of a subway, we would say that each station or node is adjacent to any other station that is just one stop away from it. We can then capture all the relations within a network by creating what is called an adjacency matrix. This is a non-mathematical introductory course, so we'll not be going into matrices, but we'll just give you a quick insight into how this is represented. We can create a simple 2x2 matrix to capture the connections within a network by placing a 1 at the cross-section between two nodes if they are adjacent, and a 0 if they are not adjacent, with the end result being a table of all the connections within the system. And this will give you an idea of what a graph looks like to a computer. Another thing we might be interested in looking at is how two nodes in a network are connected. That is to say, the channel or path through a network from one node to another, and this is called a walk. A walk on a graph is a sequence of adjacent vertices where repetition is allowed. With a walk, we are simply going from one node to the next along a sequence of edges. A path is a walk without revisiting any nodes. That is, a sequence of links from the first node to the last one without repetition. So to take a quick example of why this might be of interest to us, we could cite the so-called traveling salesman problem, which involves a salesman that has to visit a number of different cities within a particular region. He of course wants to avoid walks where he'll be retracing the same ground and try and find a path that will not involve any repetition of the cities he has to visit. There are a number of different algorithms for achieving this, but we won't go into them here. Our traveling salesman will also be interested in finding the shortest path between each place he has to visit. This shortest path between two nodes on a graph is called the geodesic, and it represents the fewest number of links that we have to traverse in order to go from any given node to another.